So let's say that I had a function that looked something like this. So we have what they call a piecewise defined function named g of x, where you have a couple of vertical asymptotes. So we have some infinite discontinuities. Here to here, this is called a jump discontinuity. Here, this is called a removable discontinuity, sometimes referred to as a hole. Now, let's suppose that the following is the goal. So we want to know the value or the values of c for which the limit of g of x as x approaches c happens to exist. So here is how I would look at this problem. So I made up some problems here that I want to quickly run through. This will not take long. And then once we've looked at these, we'll answer the main question. So over here, the limit as x approaches -4 from the left of g of x. G of x refers to this diagram. -4 is here, but we are approaching it from the left-hand side. That means left, this means right. So from the left means from this side. So I'm walking toward it in this direction. So -4 is here. I'm approaching it from the left. And as I get closer to -4, I follow the curve. I am going to go down to -infinity. That's why that limit is -infinity. How about -4, which is here, but this time we're approaching it from the right. So from the right is coming at it from the right. So here, this is where I want to go, and I'm approaching -4 from the right, and what happens? I am approaching -infinity. That's what happens to my y-coordinate. They're approaching -infinity from both directions. So here, when it says -4 without a specific direction, that implies that you're encompassing both sides. And as we just saw, from both left and right, as we approach -4 from both sides, the y-coordinates go down to -infinity. So the overall summary for -4, the limit of the function would be -infinity. How about here? We have to approach -2 from both sides. So here's -2. As I come at it from the left versus from the right, notice that my fingers are not going in the same direction. One of them is stuck here and the other one is stuck up there. So for that reason, the limit here at -2 does not exist. -2 from the left would have been a y-coordinate of -2, whereas -2 from the right, which is here, that would have been a y-coordinate of +3. But overall, from both directions, it doesn't exist because there is inconsistency in what we are approaching. How about +3 from both sides? +3 is here. So we have to approach it from both directions. Coming at it from the left goes up, coming at it from the right goes down. So again, the limits are in disagreement, so it does not exist. How about as we approach 6? 6 is here. We're approaching it from both directions. So we're coming at it from here, and then we're coming at it from there. My fingers meet one another, so we're good. The limit does exist. What is the limit? Well, whatever the y-coordinate happens to be at this location, which is -2. It does not matter that the intersection is a bit abrupt. It's not really smooth, right? It's like here we have sort of a parabolic trajectory, whereas here it's more of a linear. So this intersection is very awkward, but nonetheless, the limit does exist and it happens to be -2. How about here? Let's approach 9 from both sides. 9 is right there. As we approach 9 from both directions, notice that our y-coordinates are getting awfully close to 2. Even though there is a hole there, the y-coordinates are approaching a height of 2. The function g is not defined at 9 because there is a hole, but the limit does very much exist, and it happens to be 2. How about here? We're approaching 5 from both sides, function g of x. So 5 is somewhere in here. I didn't mark it per se, but I don't have to, because I know it's something between 3 and 6, more like right here. But notice that this entire general area is totally fine. Let's say this is 5 right there. As I approach 5 from both sides, my fingers are approaching the same value. So I don't know exactly what it is. I mean, I just made up this graph, right? But I can tell you that at 5, the limit I'll just say that it exists because I don't explicitly pick like a y coordinate for it, but I think you're getting the point here. How about this? Negative infinity. Negative infinity as an x coordinate means move to the left. So I jump on the part of the graph that gives me the option to move very far left, which is this piece here. As I move to the left forever, it seems as though this graph is sort of going upwards in an upwards trajectory. Again, I just drew this graph, I just doodled it. But as I go to the left, it seems like the graph is going up. And so this limit would be positive infinity. So now what the original question wanted, I think it's easier if you tell me where the limit does not exist. Where does the limit not exist? Well, I have some examples here. The limit did not exist at -2, and it did not exist at 3. So where else does it not exist? Find points where if you approach it from both sides, your fingers don't meet. So this part is okay, because as I go from the left and right, my fingers are meeting. Here, this is bad, because at -2, if I approach from left and right, my fingers are not in contact. That's no bueno. So let's just make a little list here. Where does it not exist? The limit doesn't exist at -2. Here at 3, it's no bueno. At 3 is no good because at 3, left and right, my fingers are not meeting. This is okay because left and right, my fingers meet. That's okay, left and right, my fingers meet. Everything after here is good. Everything before this is good. So the only places where it's bad is here and here. So where does it exist? Well, it exists everywhere except here and here. So we're talking from negative infinity to -2, union, -2 to 3, union, 3 to infinity. So as a summary, the C values for which the limit exists happens to be all of these here. I answered it as an interval using interval notation. So there you are. That's how a problem like this can be looked at.